Well, good morning, class, and welcome to the chapter 40, where we're going to be discussing the design conditions that we see on our particular units. Now, AHRI has to do with American Heating and Refrigeration Institute. And what they have done for us is they have set certain parameters that they test equipment outside with. So manufacturers will give their piece of equipment to testing facilities. Either they'll do it in-house or send it out to themselves, and then they'll get nominal BTU ratings on them, or nominal British thermal units and capacities that these units will be running in. These AHRI conditions are 95-degree outdoor temperature, 80 degrees indoor temperature, and then a 50% relative humidity when we're looking at the AHRI standard conditions for ACs that are out there. They will run their air conditioners at these conditions, and then they'll come up with a BTU capacity for these particular systems that are out there. Now that capacity could be 18,000, 24,000 BTUs, 30,000 BTUs, and so forth and so on. But when the manufacturer gives you the values of these systems, they are actually running them at 95-degree outdoor temperature. Now, since most of the time the AC will not be running at that 95-degree outdoor condition, it will actually run more efficient and the cooler temperatures because it's not dealing with the head pressure on those particular units themselves. Now, when we are dealing with the comfort of individuals, relatively 80 degrees is a really warm temperature for us to run our houses at. So what we want to do is design these systems to run at a 95-degree outdoor temperature, 75-degree indoor temperature with a 50% relative humidity value. And most people are going to be comfortable at that temperature value, especially if you're running these systems at 50% relative humidity on them. So just remember that when the nominal capacities of these units are given to you, they are actually given to you at the AHRI standard conditions for those systems. So one of the ways that we can predict or check how a system is operating is by the condensing temperature over ambient of our particular units. For the purposes of this class, what we're going to be doing is we're dealing with a lot of 13 to 15 SEER units, R410A, and we're dealing with a lot of 6 to 10 SEER units, R22. So the two numbers that we will use to predict what the high side pressure is going to be running will be the 30-degree over ambient, condensing temperature over ambient, and also, the 20-degree over condensing temperature over ambient. Now, what does that mean? That means that if it's 80 degrees outside or 80-degree ambient temperature around your condenser, and we were dealing with a 410A system that was 13 to 15 SEER, then we could predict what that system would be running on the condensing temperature if we were to add 20 degrees to that 80-degree outdoor temperature. So really, the outdoor temperature dictates what the pressure and temperature relationship is going to be on the inside of the condensing unit. And we can predict that. 80 degrees plus 20 tells us that our refrigerant will be turning into a liquid on the condenser at 100 degrees. Now we can use that to convert that temperature to a pressure and then find out if our systems are actually working correctly. 16 SEER and above, we're going to be dealing with 15 degrees. And as you continue to increase that SEER rating and that SEER 2 rating on these pieces of equipment, we're going to be increasing the size of those condensers to gain efficiencies for the government, what they were looking for us to do. Now, what makes a unit more efficient to run than other units? Well, technology has a lot to do with that. Inverter technology, the ability for us to ramp the compressor up and ramp the compressor down. avoiding the turn off and turn on of the actual compressor. Um, Also, the increase in the size of the condenser would also go into our units and our unit's ability to um, get rid of heat. If we can drop the head pressure down on these pieces of equipment, well, then our compressors don't have to work as hard against outdoor temperatures that would cause them to increase in amperage. So, technology has a lot to do with it, and also system design has a lot to do with the efficiency ratings of systems. So if you run into a system that has an inverter compressor, obviously it's going to be a system that's a higher efficiency. We have noticed over the past couple of years that our condensers have actually increased in size, where they're almost the same size as a human in the height of them, and they're doing that so that we can drop the head pressure, increase the subcooling on these units. And so that they run more efficiently. Now, when we're dealing with design conditions of the condenser, like I talked about before, 95-degree outdoor air is where our systems are designed to run at. Do they run at those temperatures? Maybe 1% of the year, but beyond that, we are still going to be running at cooler temperatures. So let's say that we had a standard efficiency unit between 6 and 12 SEER, and we had 280 psi on the high side. Well, what we would want to do is take ambient temperature, uh, and then we would add 30 degrees to that ambient temperature. So 95 plus 30 would give us 115, 125 degrees on the high side, and that'd be our condensing temperature. And then we would convert that back to a head pressure. And we would find that for a standard efficiency unit running 6 to 12, running R22 inside of it, that we would be running roughly around 280 psi on that system. Now, if you had a high efficiency unit, and they used to make R22 units that were high efficiency units that were out there, we would find that we would do 95 degrees outdoor temperature plus 20 degrees. So in that case, if we were running an R22 system, we could see that uh, by dropping the condensing temperature over ambient, we've actually dropped the pressure, which is going to drop the amp draw on the compressor. So on those types of systems, we're going to be running about 250 for an R22 system. For a 410A system on the high side, if it was 95 degrees outdoor temperature, we'd be running close to 392 psi on the high side. And if it was a 454B, which you guys are going to be running into this more and more within our industry, it would be 370 psi's for the high side of that system. Now, dealing with, remember that condensing temperature over ambient is a way for us to predict or to find out if the system is actually working like the system said it should. So you change the ambient temperature, you change the condensing temperature of that refrigerant. So if you were dealing with an 80-degree outdoor air, well, you'd have a 100-degree condensing temperature for your higher efficiency units, and you'd have 110 degrees condensing temperature for your standard efficiency types of units. So when we're actually speaking to design condensing temperatures, the condensing temperature over ambient has to do with the refrigerant on the inside of the condensing unit. And when we are referring to the actual temperature difference that we're looking at between the ambient temperature and the outlet temperature on the condensing unit, well, on a standard efficiency unit that's running R22, we might only see a 15-degree temperature difference between the ambient temperature and the discharge temperature. And that can be figured because 95 plus 15 plus or minus 3 degrees, we're going to be running somewhere between 110 degrees on the outlet temperature of that condenser. Now, understand that condensing temperature over ambient is different than temperature difference that you're going to be seeing on the condenser itself. On a high efficiency unit, that's a 13 to 15 SEER, which is most of your 410A systems, 95-degree inlet condenser plus 10 degrees. So those will be running about 105 degrees on the discharge temperature coming out the top of the condenser itself. It's just another way for us to go through and check to see how our systems are doing. We could actually use these numbers and do a BTU calculation on them, just like you could use these numbers on on an evaporator coil to do a BTU calculation on it. Either one would be good. But when we talk about the temperature difference coming off the outlet of the systems, we're going to be looking at 15 for our R22 units. In our 410A systems, we're going to be looking for like a 10-degree difference coming off the top of those condensing units. Okay, so let's look at the condensing unit on our systems themselves. This is what should be happening with that particular unit out there. So if we're dealing with an R22 standard condensing coil, it's 125-degree condensing temperature for the refrigerant inside of the unit itself. For a high efficiency unit, we'll be doing condensing temperatures of 115 degrees if our outdoor temperature is 95. Somewhere we should have, if we're dealing with the TXV, we should have a subcooling of 5 to 15. If you're dealing with a piston metering device, that subcooling, we're really not concerned with that subcooling number. We're going to be dealing with superheat values there. If we look at the temperature difference across the outdoor coil, we're going to be dealing with 15-degree air for our standard efficiency unit, 10 degrees for our high efficiency unit. Your compressor, the rating that's on the outside of the unit that says your compressor runs at this certain amperage. Well, guess what? At a 95-degree outdoor temperature, we're going to be running run load amps. Otherwise, if we're dealing with cooler temperatures, that compressor is actually going to be running lower amperage than what the RLA is. The fan's going to be running RLA or FLA amps continuously, no matter what the temperature is outside, because it's moving air. And when we look at the suction line coming back to the outdoor unit, it should be sweating at this point. If it is frozen, then we have other issues that we need to deal with on that one. When we're dealing with the evaporator and we're dealing with the designed conditions of the evaporator, indoor temperature, we figured it at 75 degrees. We want it to be around 50% relative humidity when we're checking our units over. If it's higher, then then it's higher, and we can't do really much about that. For an R22 system, we're dealing somewhere around 70 psi. Our evaporator coil temp running at 40 degrees, and we're going to get about 5 to 15 degrees superheat. And some of your publications out there will go 8 to 20. But if you're getting anywhere from 5 to 20 or 8 to 20, we're okay on our superheat, depending on what that temperature is inside of your unit. Temperature difference across the evaporator, looking at 17 to 20 degrees difference on our evaporator. We're dealing with the indoor unit, continuing with our evaporator on the system. The blower fan should be running at full load amps if it's running on high speed, depending on how the installer hooked up the particular unit themselves on that. All the systems out there are going to run at 400 CFMs per ton. If you're in a more humid climate, you might want to slow that fan speed down to take more humidity out of the air. If you're in a desert climate, you might want to speed it up because you're more concerned with cooling, not so much with removing the humidity from the air itself. Our coil should be sweating. We should have water dripping out of our condensate drain on our coil itself, and then that suction line will be sweating back to the unit itself. So AC applications, here we go with our standard efficiency unit. We're looking at a 10-degree superheat for this particular unit when we're dealing with a fixed bore metering device. And how does that look? So as the system is running, our last drop of vapor will end up happening up towards that upper portion of the evaporator itself. So the region in green is where the PT relationship doesn't hold anymore. The PT relationship says that the evaporator is running at 40 degrees, but we will gain up to 50 degrees on that suction line coming back to the compressor itself. So saturation temperature is 40. Actual temperature of the line coming back to the compressor is 50. We have 10 degrees of superheat value on a fixed bore type of metering device. As well, our evaporator should be sweating at this point. So we'll have condensation coming off of the evaporator dripping off of it. Because as that 75-degree air hits that 40-degree evaporator, it's going to draw the moisture out of the air, and then we're going to see a 17 to 20 degree temperature difference within that air. Continuing on the application of the R22 evaporator here, what we're going to do at this point is we're going to increase the load on this evaporator. And what ends up happening when we increase the load on the evaporator is that the saturation temperature changes on the inside of the system itself. So what we end up having is the evaporator pressure is 73 degrees on an R22 unit, corresponds to about um, a 43 degree saturation temperature. And then we can see that our superheat value on this system has actually increased from the other conditions that we can look at here. So instead of running a 10-degree superheat, we have 56 degrees on the suction line coming back to the compressor. The boiling point of the refrigerant is 43 degrees, so we have a 13-degree superheat on this particular unit. At this point, there is going to be quite a bit of humidity that's going to be drawn out of the evaporator itself at these conditions. And I know that the number is actually behind my head, but it is 13 degrees of superheat that we're going to be dealing with on that. So let's say that we have a condition where we have really high head pressure. What we're going to end up with, especially on a fixed bore metering device, is outdoor temperature kind of dictates how much refrigerant gets pushed into the evaporator itself. If you can think about an orifice or a spray nozzle on a garden hose, and you were to lessen the pressure keep the orifice size the same, and lessen the pressure on that hose, you would get less water coming out of the refrigerant out of the hose. The same principle goes into the amount of refrigerant flow in the evaporator as the temperature outside increases as well. So you are going to end up with more refrigerant inside of the evaporator if the pressure behind the orifice is pushing more of that refrigerant into the system itself. So in this condition, we have a system with a high head pressure. The increase in head pressure has increased the flow of the refrigerant through that device itself. So this system has a condensing temperature of around 135-degree condensing temperature, which means the temperature of the system is the outdoor temperature is around 105 degrees. So your superheat value will drop if that is the case on that system. On this particular unit, what we've done is increase the temperature and the humidity within the system. We're dealing with a superheat that is well up to 20 degrees. Now, we never want to charge an air conditioning system when the temperatures inside the house are exceeding 80 degrees. At that point, we want that system to actually bring the temperature down within the house so that we can go to that system later on with design conditions closer to where they should be, and then actually figure out what's going on with this system. But as we are dealing with higher temperatures, we have an 84-degree suction pressure for our R22 system. On that particular system, we are getting 70 degrees coming back to the evaporator with the charge not changing at all, just an increase in the temperature and humidity within the living environment. And we can see that we are running somewhere around 20 degrees of superheat on this system. Just because your superheat's up doesn't mean that it needs more refrigerant. Just because your superheat is not within your desired number that's in your head doesn't mean that the system isn't properly charged. The same principle goes into this. If the temperature was to drop outside and I had a fixed bore metering device system, then my superheat values would be allowed to be up into the 30 and 40 degree superheat range, just because of the lessened pressure on the backside of that fixed bore metering device is pushing less refrigerant into that system. So as the liquid boils off, it's going to turn into superheated gas at that point, and the less liquid that's in that evaporator, the more superheat that you're going to get on that system. But in this case, when we're looking at on this PowerPoint, um, high inside temperature humidity could end up being a higher a higher superheat value for our systems. Now, every system that's out there is going to come with some type of charging chart, whether it be a subcooling charging chart or whether it be a superheat charging chart. Really depends on the type of metering device that the system actually has. What is in front of us right now is a superheat charging chart. We can find we can use this chart to help us to figure out the system, what the system should be running, and to make changes as we are seeing fit on this particular chart. A lot of the charts will walk you through exactly what to do if the numbers aren't matching up with it. So make sure that you're reading all of the chart and not just reading the actual pressures and temperatures that the chart may be giving you. The chart tells you what to do if you're not within the desired temperature range on it. So what we're going to be doing is we're going to give you some fictitious numbers to go off of here. We're dealing with, let's say if it was 85 degrees outdoor temperature and we went to the inside of the house and we checked it and it ended up being 62-degree wet bulb temperature. At that point where these two lines are going to cross, it would tell us that our superheat coming off of that evaporator coil should be somewhere around 8. Now, on the chart, it says find the superheat, the target superheat on the chart. Actual section line temperature minus saturation temperature gives you actual superheat. If the superheat value is too high, if it's above that number, then this chart is actually telling you to add refrigerant. What's that doing? It's actually putting more refrigerant inside the evaporator, and it's going to lower that superheat value because you're going to fill up the evaporator with more liquid refrigerant on it. So if the actual temperature, and I know it's behind my head and you can't see it, but if the actual superheat number is lower than what you're seeing on the chart, then what we're going to have to do with that is take refrigerant out. So we need less refrigerant inside of that evaporator for that particular system to be running fine on that system. So let's go ahead and we'll look at a couple of different numbers and see what we need to do here. Outdoor temperature is 100 degrees. We took a wet bulb temperature of the indoor unit and we found out it is 66 degrees, and our superheat value for this system should be running somewhere around 8 degrees for that system itself. So that's one condition that we can look at. Condition number 2, remember, if that's below that number when you're taking this actual superheat number, we need to remove refrigerant. If it's above that number, we need to add refrigerant. And this is strictly only going to be found on a capillary tube metering device or a piston type of metering device itself, or one of those. So let's go a little bit cooler outside. We're dealing with a 65-degree temperature outside, 54-degree wet bulb temperature inside. The superheat value that we're looking at on that particular unit is going to be 10 degrees. If it's below that number, take refrigerant out. If it's above that number, add refrigerant to drop that superheat value down on that system. And that's the way that we're going to be using this chart itself. Now this third condition, we'll look at 85 degrees outdoor temperature. Oh, wow, our wet bulb temperature kind of went up. We're dealing with a 72-degree wet bulb temperature. Find out where those two numbers intersect on the graph. The superheat value that we're looking at on this chart would be 26 degrees. Below that number, take refrigerant out. Above that number, add refrigerant to drop it. Get it as close as you can. And if you got it as close as you can, at that point, there comes a point where you just got to walk away from the unit once you get it close and not fidget over not having that number perfect. So if you're close, I'd say within 2 to 3 degrees of this number, then you are good to go. You can walk away. Check that evaporator temperature drop, 17 to 20, and that unit should be cooling fine for that particular house itself. Another way that manufacturers help us to understand how to charge a system is by giving us a system with the design subcooling of that particular system. It's called a subcooling chart. This chart list is from a Trane air conditioner. The first thing that we have to find out is you can see the top portion of this line. What is our design subcooling? Where do you find that number at? Well, you're going to have to go to the manufacturer data plate on the outside of that Trane unit to find out what the actual subcooling of that system will be. And that is found right here. So our subcooling for this particular Trane unit is going to be 10 degrees subcooling, plus or minus 3 degrees, what you're looking at. You could actually go off the liquid line temperature and adjust it to 7 to 13 degrees subcooling for this unit. Or if you're having an issue with it, you can actually go to this subcooling chart and find out. So the graph that we're going to be looking at for that is found right there at the 10 degrees. So we're going to use that 10 degree subcooling, design subcooling for this particular unit itself. So take the temperature of the liquid line at this point. So we're taking the temperature of the liquid line, and we found out that our liquid line temperature was running somewhere around 95 degrees. We're looking at our design subcooling of 10 degrees. And where do these two numbers cross? Well, our high side pressure that's on our high side gauge should be somewhere around 349 degrees. Now, on the manufacturer data plate, it will tell you that if this number is below 341 psi on your liquid gauge pressure, then we need to add refrigerant to that system, which would increase the amount of subcooling happening within the condenser coil. If that number was above 341, then we would have to remove refrigerant from that system so that subcooling number would be close to 10 as possible. So when we look at this, design subcooling of 10, take a liquid line temperature, we find out that it's 95 degrees. High side pressure should be running around 341 degrees PSIG. If it's below that number, add refrigerant. If it's above that number, take refrigerant out. So we'll go through a couple of scenarios on this system. We took a liquid line temperature and found out it was 80 degrees. We found out our design subcooling was 10 based off the subcooling that our system was calling for. Our PSI on our high side should be running somewhere around 295 degrees. When we took the actual pressure of the high side, we found out it was 255 degrees. So kind of going back to what should you do at this point? It should be running at 275. It's running at 255. We're going to have to add refrigerant to bring that pressure on the high side up closer to 275 to get the required subcooling off of that unit itself. Okay, a different condition that we're looking at, condition number 2. We're dealing with a 100-degree design or liquid line temperature of 100 degrees. What is our design? Well, this time when we looked at the nameplate, we found out that the design subcooling would be 13. And what we're going to end up with is these guys crossing at 381 PSIG on the high side. So when we took an actual pressure of the high side of this unit, we found out that the actual pressure was 300 psi, well below where it should be. What do we need to do? Well, we need to add refrigerant to bring pressure up to that system itself. Let's look at another condition in condition number 3. We're dealing with a 90-degree liquid line temp. We can look at this. We have 11 degrees of subcooling told to us by the nameplate on the Trane unit or carrier when you're looking at it. Our pressure should be running at 322 psig. Our high side pressure is actually running at 425 psig. We will need to remove refrigerant to bring that pressure back down to the appropriate value. And I know I just skipped off of that page, but that's what we're going to have to do with that. So the chart that we're looking at here is a temp drop chart. And this is typically a chart that's going to be used for a TXV type of system. We're going to give you a couple of different values on here. Regularly, what we're looking at, if you don't have this chart or the system doesn't give you this chart, we want about a 17 to 20 degree drop on our temperature on our evaporator coil. So the return air coming in and the supply air coming out, we want about a 17 to 20 degree drop. Now, if you can figure out what the return air dry bulb temperature is and what the return air wet bulb temperature is, well, now we can figure out exactly what that temperature drop should be on that particular system. So we'll throw a couple fictitious numbers out there for you. We took a reading on the return air. We found out the wet bulb temperature was 63. We found that the dry bulb temperature was 75. Okay, and our expected temperature range should be plus or minus 18.6 degree drop across that evaporator coil itself. So if the system is not within this range, it could be many issues ranging from the charge of the system, airflow, dirty coil, dirty fan, dirty secondary heat exchanger. It could be that if we're getting a drop of over, 18 degrees, well, our airflow has significantly been decreased to cause that to happen. So we're looking at that 17, 18.6. So if it's above that, and we're saying like 25, look for airflow. If it's below that, look for charge. It probably a charge issue if that's the case. And the other one's probably due to an airflow issue on it. If it's a charge issue, add charge. If it's an airflow issue, fix the airflow issue itself. So condition number 2, what we'll look at is 61 degree wet bulb temperature, and we find that using a sling psychrometer. The indoor dry bulb temperature is 75, and we find out that the temperature drop on the system should be somewhere close to 19.9. Now, if it's below that number, it's a charge issue. It's above that number, it's an airflow issue. So check for those. Third condition we'll look at here, expected temp drop on this one. We have a 63 degree wet bulb temperature, 80 degree dry bulb temperature. We should be getting somewhere close to 21 degrees on our temp drop. If it's above that, then we're looking for airflow. If it's below that, we're looking for charge issues on that. But this is a nice chart for us to look at. We'll look at one more condition for these systems themselves. 77 degree dry bulb temperature. We're dealing with a 74 degree wet bulb temperature. And we see that the temperature drop of our evaporator should be somewhere about 9.4. The reason for that is a lot of the BTUs is being eaten up by the condensate. The removal of the moisture out of the air with a wet bulb temperature exceeding the normal on that, giving us a 74 degree wet bulb temperature expected to be 9.5. Below that, we got a charge issue. Above that, we're dealing with some sort of airflow issue on that. So on a capillary tube system or a piston metering device type of system, to predict what that system's superheat should be, another way to do it is take 105 degrees minus the ambient temperature. And this is why I screwed this up when I was out in the field. When it was you look at units and you charge them no matter what the temperature is outside. So I went to do service calls and it was 60 degrees in the morning, 80 degrees in the afternoon. Well, if you're taking a unit and it's 60 degrees in the morning and you have a capillary tube or a piston type of metering device, well, your superheat value could be somewhere up around 40 45 degrees. And as a new service tech coming out into the field, I looked at that number and go, no, 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 I can't have that. This number should be 8 to 15 or 5 to 15. So I added refrigerant at that point to drop that superheat down. And then when it got warmer out, that system was significantly overcharged, and they had to go back and remove refrigerant on it. So a mistake that a young service tech made that you don't need to make as an old like, as a young service tech because you've been told. But if you want to predict where that where that suction superheat should be, or where that superheat value should be, take 105 degrees, subtract your ambient temperature, and then that's your target superheat for a capillary tube or a piston style metering device. I hope you guys learned quite a bit about what the normal conditions should be for an air conditioner. And hopefully we'll get to chapter 41 so that we can talk about troubleshooting these AC systems and figure out what's going on with them. Stay safe out there.